Hello, this is AMET 104 lecture recording week 11.3. So until last time we went over chapter 16.3 regarding probability, and we looked at several different examples. Today we're going to look at more examples on the chapter, and we're only going to look at 3 different examples. So hopefully today is going to be a little shorter recording than usual. So let's get into the examples. So let's say 7 horses, and we're gonna name it for the sake of the problem A, B, C, D, E, F, and G. Are running in a race. And according to the odds makers, the horse A has 3 in 20 probability of winning. And B has 7 in 20 probability of winning. So 7 in 20 probability of winning. And let's say C has 3 in 10 probability of winning. And lastly, the remaining horses all have the same probability of winning. And here we are to find the probability assignment for each horse. So how would we do that? So before we do anything, we're already given a few horses. So in this case, we know that even though we're given in words, we know that the probability of horse A winning is 3 in 20. So I'm just going to write it 3 over 20 mathematically. And we also know that the probability of B winning the whole tournament, the race, is given as 7 in 20. But we're also given the probability of C winning the tournament as 3 in 10. And one thing we know about the rest of the horses is that the probability of D is equal to the probability of E, probability of F, and they're all equal probability. So they're equally likely to win. So knowing that, how would you find out the probability assignments for the rest of the 4 horses? So one thing that we established so far in the past two classes is that probability assignments do add up to be 1. So this implies that since the probability adds up to be 1, so probability of A, probability of B, probability of C, probability of D, probability of E, F, and lastly G altogether has to equal to 1, and that's one thing we know. And actually that's all we really need to know, because we can simply substitute all the numbers we know. So for probability of A, we know that it's 3 over 20, plus for B, we have 7 out of 20. For C, we know it's 3 out of 10, and we can write the rest like this. And let's actually say that in this case, let's assign it to be just a P, because it's going to take a lot of time just to write all 4 like this. So in this case, we know this is a P, whatever that assignment is, they're all the same like this. So we're just denoting it to be some probability P. So let's now do some calculation. So we know that in order to add the fractions, we need to have a common denominator. And I assume you guys know how to do that already, but just to quickly go over, the first probability is 3 over 20, second is 7 over 20, the third is over 10. But we need to have the same denominator. So in order for 10 to have the same denominator, you simply multiply 2 in top and the bottom. So you'll have 6 over 20, and that's the same thing. And since we have 4 of the probability P, let's say it's just 4P. And I'm sure we can all agree with that. So let's simply do the addition here. So since we now have all the same denominator as 20, we now have 3 plus 7 plus 6 over 20. So 4P equals to 1. And that is, the top is 16 over 20 plus 4P. And if you subtract 16 over 20 on both sides, we actually have 4P equals to 1 minus 16 over 20. Wait, so 1 is also not in the common denominator 20, but we also know that 1 is simply 20 over 20 minus 16 over 20. And that simply implies that 4P is simply 4, I don't know why I wrote 12 there, but it should be 20. So 4P is simply 4 over 20. And now by simply dividing 4 on both sides, we can end up with the simple probability P is now equal to 1 over 20. So what does this imply? This implies that probability of D, E, F, and G, they all equal to 1 over 20. And that's really all there is to it in this problem. So the only thing we really used was the fact that the probability assignments do add up to be 1. And that's really all you really needed to solve this problem. So let's now go over to the next example, the second example. And let's say An honest coin, or a fair coin, a lot of people would say, is tossed 5 times in a row. And you have to find a probability of following events. So let's say the event 1 is defined as the coin comes up, heads exactly twice. So out of 5 times, you now have exactly 2 coins. So there are a couple of different ways to go about solving this problem, but let's first do the counting. I'm not sure if you want to call it a longer way or the easier way, but let's do the simple counting. So we know that out of 5, we need to count the number of heads to be exactly twice. So you can have heads, heads, tail, tail, tail. That's 2 heads. You can have heads, tail, heads, tail, tail. You can have heads, tail, tail, heads, tail. You can have head, tails, 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 heads. And you can have tails, heads, heads, tails, tails. And tails, heads, tails, heads, tails. Tails, heads, tails, tails, heads. Tails, tails, heads, heads, tails. Tails, tails, heads, tails, heads. And lastly, you can have tails, 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 heads, and heads. Was it easy to follow? But I think that's all we can do with out of 5 tosses, we have exactly 2 heads. So how do you find a probability? So the probability assignment is simply found by the number of outcomes divided by the number of total possible outcomes. So when you're tossing 5 coins 5 times, we can simply say the sample size is given as the first coin can come in 2 different ways, second coin can come 2 different ways, 2, 2, and 2. And it simply is that each coin has 2 different possibilities, and you're simply doing it 5 times. And that is 32. We've actually went over this calculation before, and just to briefly go over, it simply implies that the first coin can land in 2 different ways. You have 2 different possibilities for the first toss. You have the 2 different possibilities for the second toss, third, and fourth, and fifth. And simply, this is a multiplication rule. And if it was, let's say, rolling a die 5 times or rolling 5 dice, you should have done the 6, because for each roll you have 6 different possibilities. So you have 6 to the power of 5. So in this case, it simply implies that for each toss, you have 2 different possibilities and you're tossing 5 times. In total, you have 32. And we did go over this before. Then, since we have 10 possible outcomes such that the head comes up exactly twice, then we can simply conclude the probability of E1 in this case is 10 over 32, or you can simply simplify it to be 5 over 16. Let's now look at the, before we do that, so we could have done this way, Or we also could have used the combination. So another way, the combination. So combination in this case would be out of 5 tosses, combination you want 2 to be the heads. So it's going to be 5 factorial over 2 factorial over 5 minus 2 factorial. And simply that's going to be 5 factorial over 2 factorial multiplied by 3 factorial. And that is 5, 4, 3, 2, 1 divided by 2, 1, 3, 2, 1. And obviously you can cancel these out. So it's going to be 20 over 2. So that's 10. So without having to count each one of them like this, we actually concluded that there are 10 different possibilities where the heads comes up twice. We also did go over the combination in, I think, last week, and I basically mentioned that it's not really necessary because all the problems that you're going to encounter will be able to will be small enough numbers where you can actually count something like this, but it's going to make your life a lot easier if you knew how to do this. So practice if you think it's necessary, and I would really highly encourage you to do so. But if you really want to opt out, you sure can. But I would like to mention that if you were counting things like this, you are bound to miss 1 or 2 outcomes, and you may not have the correct number. And at that point, it's really not anybody's fault that you have a wrong outcome, wrong number of outcomes, because you'll probably have to do it over and over again until you actually get the correct numbers. Okay, so now let's look at the second event. So we're still tossing the coin 5 times. So let's say the event 2 is now defined as all 5 tosses come up the same. So what does this mean? So all 5 tosses come up the same. So for each toss, you can either have heads or tails. So this implies that all 5 tosses comes up either all heads or all tails. So you have heads, 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 or tail, 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 tail. And you only have 2 different possibilities. So since we know there are a total of 32 possibilities, so total of 32, we can simply conclude that the probability of E2 in this case would be 2 out of 32, and by simply simplifying it, you have 1 over 16. I think that was simple enough. Now let's look at the third event. So this one says exactly half of the tosses come up tails. So what does that mean? Exactly half the tosses come up tails. So in this case, this is not possible because there's no exact half outcomes when you're tossing odd number of times. So you can either have twice or 3 times, but there is no 2.5 times of tails. So in this case, we know that this is an impossible event. Impossible event. And that's something that you should be able to conclude yourself. So hence, you can see that the probability of E3 is simply 0 because it's not possible. So it's 0 over 32. The next scenario, let's say the first 2 tosses come up heads. So the first 2 So what does this mean? This means that out of 5 spots, you have first 2 that's designated for heads, and the rest could actually be anything. So this is actually simple because this means that for the 3rd spot, you have 2 possibilities. For the 4th, you have 2, and the 5th, you also have 2. So this implies that this is 2 to the power of 2 to the power of 3, and that is simply 8. So hence the probability of E4, you can simply say that this is 8 out of 32, and hence it's 1/4 probability. So now let's look at the next example. So this is likely going to be the last example. So in this case, let's say a student randomly guesses the answers to a four-question true or false quiz. The observation is the student's answer. In other words, we want to see either T or F that they have guessed. And here we're going to look at the following events and the probabilities. So let's say for the first event, let's say the student answers F on 2 of the 4 questions. And in this case, let's actually do the combination method. And we know that we're choosing 2 out of 4. So this is simply 4 combination 2. And this is going to be 4 factorial over 2 factorial multiplied by 4 minus 2 factorial. And that is 4, 3, 2, 1. And that's 2 multiplied by 1. And 4 minus 2 is 2. And also it's 2, 1. We know that 2, 1 cancels out here. And hence we have 12 over 2. So it's 6. So we know that there are 6 different ways that the student answers F on exactly 2 of the 4 problems. Let's actually check. We can actually confirm that by FFTT, FT, FT, FTT, F, T, F, FT, T, F, T, F, and lastly T, T, F, F. So we have 6. We can confirm that this is true. Then how many different ways can the student answer this problem? So what's the sample size? So here we know that the sample size is, as you all may know already, it's 2 to the power of 4 because we have 2 choices for each answer and we are doing 4 times. So simply this is 16. So now this implies that you have the probability of E1 is now 6 out of 16. Or in other words, if you simplify it, it's going to be 3 out of 8. Let's now look at the next event. And let's say this one is the student answers F on at least 2 out of 4. F-O-U-R. So what does it mean by at least 2? It means that 2, 3, and 4. So in this case, we can see that there are more, it's more likely to have the student guess at least 2 out of 4 Fs than not. So in this case, we're going to approach this problem a little differently. We're going to count the complement. So complement would be answers 1 or 2, no, actually 1 or no F. Does that make sense? So this is simply the complement statement, or in other words, it's a statement that's exactly opposite of what this event is talking about. So this means that the student has 0 or 1 Fs in their choices. So let's actually count this because it's going to be a lot smaller number. So in this case, we can see that having no F is simply all T. And we've already done this. So that was simple. And having 1 F would be F, T, 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 F, T, 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 F, T, and lastly T, 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 F. And that's really all there is to it. So instead of counting the number of at least 2 Fs, it's actually a lot easier to count the complement. So this is an intuitive decision. you could go ahead and count the number of outcomes for this exact event, and there's nothing wrong with that. And in this case, I just thought this will be a lot easier to count. Counting 5 is a lot easier than counting 11. So why is it 11? Because we know that this is a complement event. So if we denote that this event to be, let's say we denote this event to be F1 event, then the probability of F1 is 5/16. And since it's complement, it means that the probability of E2 plus the probability of F1 is 1. And since F1 is 5/16, we can simply subtract 5/16 on both sides and conclude that the probability of E2 is 11/16. And as we can see, there would have been 11 different outcomes. Sure, 11 is not a huge number, but it is bigger than 5. So in this case, I just thought that it would be easier to do this, but there's nothing wrong with going about counting 11 different outcomes. Let's now look at the next event, E3. So this one is the student answers F on at most 4 out of 4 questions. So what does this mean? If a student answers at most 4, so if a student answers at most 4, this means the student answers either 0, 1, 2, and 3, and 4. So at most 4 includes everything before. So what does this mean? So out of 4 questions, a student can either answer 0, 1, 2, 3, or 4 Fs. So in this case, this is actually implying any type of scenario. So in this case, we can see that this is the actual sample size. So it means the sample space. So this event is the sample space, entire sample space. And hence we can say this is a probability of E3 is simply 1. Now let's look at one last example, E4. Let's say the student answers F to the first question. So this is actually a very similar problem to the coin toss problem that we saw earlier. So out of 4 spots, we are already given that the first spot it has to be F. So we don't have to take care of that at all. But for the second, third, and fourth, we each have 2 different possibilities. And by multiplication rule, we can say that this has 8 different outcomes. And hence, since there are 16 total outcomes, the probability of F4 is simply 8/16, which is 1/2. So that's actually all for today. Next class, we're going to go over the next chapter, which is going to be 16.4. It's going to talk about expectation, which is a similar concept to average and mean, but it's a little bit different. It will involve more computation, multiplication than counting. And so that's it. Thank you for joining the class, and I hope you have a great rest of the day.